Let's take a look at a problem regarding a volume of revolution. So in your homework, each time you see the problem, you will not be able to set up your integral to solve unless you have a good visual picture of what's happening. So we certainly know our square root function. And we've got a boundary also at x equals 4. That's a vertical line. And a third boundary at x equals 10. So you might say, well, why those numbers? And there's probably no reason. Here we have a simple point. We know the square root of 4 is 2, but the point here might be to remind you that we don't always know the square root. But we want to take this region, and notice it's also bounded by y equals 0. That's the x-axis. So let me grab a highlighter here and shade. This is the region that is bounded by those 4 functions. But now we're not just interested in the area. Notice that what we're doing now is we're going to take this region and revolve it about the x-axis. So let's switch to Geometry Sketchpad and Mrs. Weeks' excellent Calculus in Motion demonstrations and see if that gives you a good idea first of what this is going to look like when we do this rotation. So here we've got exactly this same graph of x squared and our region going from a at 4 to b at 10. And let's put this animation here in motion and see what happens if it turns out to be what you expected it to be. Sort of cylindrical, but having various radii. So if you think about, let me just stop this for a second and reset. If you think about what happens here, if I can grab this x coordinate and my stylus isn't cooperating, we can see that the radius of each of those cross sections is growing as we sweep across. So let's get that picture again of that solid shape, and it is solid. And notice this black figure represents one typical disk. So let's just stop the revolution here for a second, and then let's sweep that disk so you can see that each cross section would look like a coin, but it's getting larger as we sweep from left to right. Well, if we know how to write a formula for one of those cross sections, then integration serves the purpose of accumulating all of those cross sections. So the calculus problem becomes much more simple than perhaps you thought it would. Okay, so let's just stop this, and then let's go back and see if we can set that up. And I've already captured a picture of that revolution, of that volume of revolution, and it's what we just drew a minute ago. We're going to go from 4 over to 10, and here's our typical cross section. So we had this point labeled at 4, 2, and we had this point labeled at 10 square root of 10. But what about this point right here? Well, remember that that disk has to move. Our integral to find our volume is going to move from 4 over to 10. So we need a variable. We can't do a fixed value here. So we say, well, for any generic value of x, what would be this distance? And of course, that comes from the formula of our function. It is the square root of x. So do you see that that becomes the radius of this typical cross section? That cross section, if we would lay it down flat here, would just have a very thin value here. And in geometry, we would have called that a cylinder with a very short height. So the height of that cylinder here we would call our delta x, or our dx value. And the volume of a cylinder is the cross section times the height. So you're not going to have to repeat this every time. You'll get used to remembering this. So our height is that very tiny value, dx. And our radius of this was our square root of x. So each one of these, whoops, I wrote the square root of 2 there. Let me see if I can get that fixed. Square root of x, that's our radius, but we need to square it. We need to square the radius, and then our height was our dx value. So this is one typical cross section. This is how we would find the volume of one of those black discs in our diagram. So what do we do if we want to have that disc sweeping across our diagram? We want to simply put it into an integral. So we want to add up all of these discs. And of course you guys wouldn't write this. You square root of x squared, you would change to an x. And you will probably also immediately get used to moving your constants out in front of the integral. So I've simply squared the square root here. So we're almost finished. It's a much simpler process than you maybe thought it was. Antiderivative, I raise the power and I divide by that power. And then we want to evaluate from 4 to 10. Let me get a little space to write here. So I'm going to move that half out with the pi for now. So I would have x squared at 10 minus x squared at 4. So it looks like we've got 84 halves, or 42 pi. And now this, we don't have units given in this problem. I don't believe we said any specific units. So we'll just tack on cubic units.